Okay. Okay, sound is working. Okay, thanks for coming to my talk. I know Venkat is in another room here, so it's hard to compete with him, but we got a good room. So it's the first time that I give this talk, and I test it. We're gonna talk. I will give it. It's a 3 hours talk. My goal is to have a break, more or less in the middle, 50 minutes. But when I was rehearsing that, it took me. I can talk for 5 hours. I can do that in 5 hours. I test on my kids and wife. They were sleeping after 30 minutes. So I watch out for you guys and girls, who is sleeping or not. But take your time. Take a nap if you want. So let's see what is the agenda today. So I split it. Actually, I submit 3 talks to the Vox. This one got selected. The other 2 were actually one about event-first design and building event-sourced applications, and the other one about building, achieving consistency in distributed systems. And then I said, okay, if I merge those 2 talks and maybe submit an in-depth talk, it can also be accepted, and that is what happened. So actually, what you're going to see here is 2 talks that I have, that I merged, but I have more time here. I have 3 hours, so normally it's 50 minutes each of these talks. So I will take more time, just go more in detail and so on. If you read the abstract in my bio, I work for Lightband. If you don't know who knows Lightband, maybe you can see their hands. Okay, so maybe who knows Akka? Okay, more people knows Akka. So Lightband builds Akka. So I work on the Akka team, and we do lots of other things related with distributed systems, but also with event sourcing. And we have for 2 years now, we launched a new product that builds on top of Akka, but it's more high-level abstraction to build event sourcing system. But my talk is not about Akka nor Calyx, is the name of this other product we have. It's not about that. I will talk more about the main principles, what is inside, not only in the products that we build, but also other frameworks that are out there to build event source systems. The goal here is that you understand what is the machinery behind it and the motivations why we do that. And if you understand how it works inside, and if you need to build an event-driven architecture, you understand what is happening behind it and what are the principles that you have to follow to have it a well-oiled machine. So maybe a question, who is now today building event-driven architecture in microservice? Okay, well, and seems like half of the room and you came to my talk. Are you having trouble with that? I don't know if you came here to verify if what you're doing is solid or not, if you have troubles or not. Anyway, let's see where we go with that. So I will split here. I will first talk about event-first design, event sourcing, projections runtimes. Then, because it's a 3 hours talk, so let's take our time. We make a break, more or less in the middle. And then when we come back, let's say 15 minutes break, and then when we come back, I will talk about how to keep things consistent in a distributed system. I will briefly talk about the existing frameworks, also our stuff, but also other existing frameworks out there, and a little bit about some patterns that I have seen in my career. I worked for Lightband. I worked for Lightband for 6 years. Before that, I was already doing event sourcing and so forth. I worked for the Flemish government here in Belgium, where we did a lot of event sourcing, and even before that. Anyway, so I have seen a few cases that the cases that I always use to tell people what not to do when building event-sourced applications. Let me see if this is working here, because I will probably work around a little bit more. So before we start, let's go back to traditional applications. And I guess that everybody here knows what I'm going to say here. It's very, very classical. So that's how I depict a monolith application. So in Java, we generally we build our models, And let's say we have those are all classes in my application. They can communicate with each other. They can be, I can call methods from one to the other, whatever. They are all in one single application. And I also build a model that I need to design the database tables where the data from my objects will be stored. And I will use something like JPA or Hibernate or any other object relational mapping framework to read data from database, drop that data in my objects, I manipulate the objects in memory, and then I flush data back. That's classical, that works. That's how we have been building applications for a very long time. And let's imagine that I'm still in the same application here, and I have the use case where whenever shopping cart is checked out, by the way, just go back. I'm not pretending here to be an expert on e-commerce. I just drop here some names. If you're building an e-commerce application, you probably looked at it that doesn't make sense, but it's just illustrative, okay? But let's go back here to my other slide. Shopping cart. Whenever a shopping cart is checked out, I need to create an order. And that's easy, because I initiate my shopping cart, I get the checkout, I set a Boolean flag to true, I create an order, and I do it in one single transaction. I'm done. This is easy to do. The thing is that next people say to you, let's build a microservice. And now what before were different service or objects in my application, they are now split over different JVMs, over different machines, and so on. And what was before one single application where I could have a single transaction, now I have different process running. I can have different nodes, I can have different nodes for each of those, and so forth. So, and in between them, to let them communicate with each other, I need to use some API, REST call, RPC, gRPC, anything that could allow me to let data be transferred from one side to the other. And now if we go back to our previous use case, I don't know if you remember before I had one red container. Now I have two because there are two different applications. They have their own database. But now I have a problem because when I want to check out my shopping cart, I need to create an order, but it's another process. So I save my transaction on the shopping cart service, and now I need to go create an order. But if the order is not running, well, now I have a checked out shopping cart, and I don't have an order because I have two different systems. One can be down, the communication can fail, the network can fail, and so forth. So how to solve that? And I think this is not a secret for many people here, but unfortunately, I still see people doing the following. Let's create a table. And let's put, whenever I check out a shopping cart, I will save here on this table, and I will try to create the order. And if it passes, I say that the order is created. If not, I will have a background job trying that again and again. And I will be polling this table, and every time that I see true and false, it means that the order was not created, and then I will try to create the order. And this kind of little bit repetitive, and it's an ad hoc solution, so I have to build such a thing for this use case, for this specific situation. And imagine if you need to create yet another object. Now you have to put another column on this table, and so forth. So this is all very clunky. And that's, of course, not the way to solve that. But unfortunately, we still see people building applications like that. So what we want, and I guess you all saw where I was going to, we want to have event-driven microservice. And the idea here is to put events as a central piece of our architecture. So build a system that can communicate, that the fabric, the way to communicate between the different parts are through events. So to do that, we need to start producing events. And there are lots, the events is quite overloaded term. And we talk about event streams, we talk about event-driven, we talk about event sourcing, and so forth. And so to produce events, there are many ways of producing events. Today, I will only cover event sourcing. And the reason is that there are other techniques like change data capture, where you use some tool that connects to your database and watch for the write-ahead logging, which is most databases offer this kind of functionality where all the transactions are written down, and you analyze that, you watch it out, and you infer from what is put there. You produce events from what you see there, from what is inferred from the write-ahead log. In most cases, these are just CRUD operations. You just have a CRUD model where you're just writing, and then every time that something is written, the write-ahead log will have a representation of that using some tools like the Bayesian, you can read it and produce some events to some other formats to be sent to some other place. Another technique is to use transactional outbox, which is a combination of having an event store and a CRUD model. So in one single transaction, you have your CRUD model as usual, like with using JPA, Hibernate. But you have also a table in your system where you write events. And whenever I update a model, I will, in the same transaction, write something in that table that I use to send it to some other place later on. That's all good, that works, and that can be a good solution for the systems that you have right now. But in both cases, the events are not the first-class citizen. They are as an afterthought. They are inferred from the CRUD operation. While in event sourcing, and that's an important distinction, when we talk about event sourcing, it's not just about event-driven applications. You can have event-driven applications without event sourcing. When we talk about event sourcing, is that the primary consumer of the events are the model itself, your domain model. So when you mutate your domain model, you mutate it by producing events that are then applied to your model and mutate it. And by doing that, you end up with an event journal. And once you have this event journal, you can then go the next phase, the next step, and use that journal to propagate data to other systems. But primarily, you do that to update, to express the change in your current model inside your application. So your model is not a CRUD model. It's an event-sourced model. There is a sentence from a quote from Greg Young. Who knows Greg Young? Okay. Who knows Akka? There were more people that knew Akka than Greg Young, probably because Akka is more popular in the Java world. Greg Young is more a .NET guy. But it's the person that popularized CQRS, Command Query Responsibility Segregation. I'm going to talk briefly about that later on. But I like this quote very much, and I pick it from a presentation from Jonas Bonner, our CTO, because he put it on a presentation and said, wow, that's really good. I will pick it that one as well. So he said, when you start modeling events, it forces you to think about the behavior of the system as opposed to thinking about the structure of the system. So we all learned about design at some point in our career. And I remember when I was reading about design a long time ago, we used to say, okay, let's write down what the system needs to do. And by doing that, we were using words like a shopping cart, a user adds items to a shopping cart, a user can remove items from a shopping cart, and then the user checks out the shopping cart, and the shopping cart will trigger the creation of an order, something like that. And we would write this down, and then we would underline a few words like user, shopping cart, order, and we would use that to identify our domain objects. And that's all great, we still need to do that. But we can also try to think about the operations that can be done on those models. It's not only a shopping cart, but a shopping cart, I can add an item, I can remove an item, I can check out it. So there are the verbs that go together with my domain model that express the behavior, what can be done. And usually we will identify things that can happen, So they are usually expressed in the imperative tense, like add an item, remove an item, check out the cart, and so forth. And then things that express what happened. And those are the events. Item was added, item was removed, shopping cart was checked out, and so forth. And so you start to think or model your domain, in terms of not only the object itself, the structure of the data, but also the operations that can happen on it. And you create commands and events to operate on it. So this is all a different way of working with your domain. To think about event sourcing, I like to use the bank account example, which is everybody has a bank account here, some with more money than others, but everybody understands how it works. If I go to my bank account and I read all the transactions that ever happened on my bank account, and I sum them up, I end up with the balance that I have today in my bank account. So we start by creating a bank account. At that point, it has balance 0. So there is always a correlation between the events and the states. I can always construct the states of my bank account by reading the events. So I added money on it, $100, 100 euros, whatever. I have a balance of 100. I decrease. I have an event balance decreased by 30 euros, and now I have a balance of 70. This is a known way of working with accounts and having transactions and summing up and regenerating the state of my account. And the thing is, can we use that for everything that we have in our system? Can I explain all mutations in my shopping cart, in my order, in whatever I have, using events? So that's the idea behind event sourcing, is that everything is expressed in terms of events. And not only things like that are obviously event sourced, like transactions in a bank account, but everything can be modeled that way. So once we have a system that are emitting events, that produce events, then I have the fabric now to let data propagate from one service to another. So if I go back to that previous example that I had, whenever shopping cart is checked out, I will have something, and I will go more in detail later on, that will listen to that, listen to events from a shopping cart on that side of my application, and will publish that event to some sort of event bus. Can be whatever you want. Kafka, Google Pub Sub, there are many of those. Or even you can, well, anyway, I will go back there later on. I will not precipitate myself. Let's say that we have an event bus, and I publish my events there. On the other side, there is the other application is listen to a given kind of event, some types of events, and it will pick up that checkout event that you don't publish your events the way they are inside your application. You transform to something else, because whenever you publish an event on a broker, you have to consider that as an external API. So you probably don't want to publish the events as you have in your storage, in your journal. You want to transform that to something else. And you may not publish everything. You kind of create a contract between the two applications, and let's say that the other application says, I just need to have the checkout. I don't care about the rest. So whenever there is a checkout event, on your side, please publish in that format, and I will consume. Just an example, okay? Anyway, so the order consumes the checkout event, and now the order is created. But of course, there is a delay here, no? Previously, when we had one single application, I was doing that in one transaction. Now, I need to publish my events, and then they get published into some event bus, and then consume it on the other side. And that's what basically this kind of process is what we call a choreography. They are like dancing with each other. One is, actually there is a flow of information going from one side to the other. And but you need to have in place the tools to build this kind of system. And that's what I want to go a little bit more in detail. And at the end, what we want to have, it's instead of having a microservice where you have a point-to-point calls, you listen to events. They publish events, and the other parts listen to those events published to some event bus. This picture here will evolve a little bit later, but let's say that's basically what we would like to have to avoid RPC calls and direct calls between the service. No? And then we build everything on a foundation that we have the guarantee that the event will be transferred from one side to the other. So that's basic the whole idea. It seems easy to do, but it's not that easy. And also Greg Young, which is the guy behind the CQRS command, query responsibility segregation, he used to say that you should not write a framework to do CQRS. You do not need to write a framework to have an event source system. Well, I disagree with that. If you're just doing one small application, okay. But maybe he said that before microservices became popular. I will not build an in-house framework to do that for each of those services. I want to have a solution that is good for everything. And even if you build that yourself, and that's the goal of the talk, I want you to understand what are the basic principles. Eventually you write it yourself. But of course, be aware, it's not that easy as one can imagine. But let's go by case. So event sourcing. I think I have already said a lot about it, but one thing that I want you to understand is it's a completely different way of persisting data, and it's a completely different way of interacting with your model. If you think about JPA, Hibernate, CRUD models, well, that's totally different. To start with, you don't have this mapping between your model and some relation database. You just throw it away. You don't use it. You don't interact by going to an entity manager, fetching that from the database, and calling setters and getters on your model, modifying it, and let it go back to the database. You send commands to it, and that's important. You send commands to it. And the command needs to be validated. I don't know if you remember, I said commands are imperative tense. It's a request, and a request can be denied, can be rejected. And then once they are validated, and the model decides that it has to emit some events will be built, emitted, and they will be persisted. And they are persisted as blobs in a journal table. And why as blobs? You don't have a schema for them. Because in an event journal, you don't know, it's just a general proposed table that has some fixed columns like event type, sequence number, the idea of the model that you are manipulating, and the payload of the event. You don't have a model, you don't do a mapping from your events to some table like with Hibernate. You just persist it as blob. And there are consequences of doing that, of course, you're going to see. And once the events are persisted, we apply to the model. And that's where we should make the distinction between event stream, event-driven, and event sourcing. They apply to the model. They are emitted by your model, and they are used to mutate your model. So your model is sourced by events. The changes from your model are expressed in terms of events. Once you have this journal, you're going to use it to replay the state of your model. So imagine that I have a shopping cart or a bank account, and I want to withdraw money from that. I will first replay all my all my transactions, get to my balance, and then decide if I can withdraw money or not from that. So the journal is used to replay to reconstruct your state. And that is done, and whenever new command needs to be delivered. And then comes the event-driven part, is once you have those journals those events in your journal, you can use it to project and generate more data from that. You can consume your events and build new models or publish to the outside. When I talk about building new models, you can build other representations that can be used to query, and you can use it to publish to some broker or even consume your events to send commands to some other models. Strange because here it didn't change. No. Yeah, now I have the same. Okay. So first I want to have a look on what we can call event source runtime, event sourcing runtime. So I said that you interact differently with your model. It's not like in a CRUD application. So what's going to happen is that you define, let me see if this works. Not so good. Let me do something. That's better. So here we have what will be your model. I'm calling that an event-sourced entity, some entity. It will have state, it will have command handlers to handle commands, and it will have event handlers. And it will live at some place in your application, but we won't interact directly with that. You're gonna, whenever you need to use it, you're gonna interact with that through some event source in runtime. And that's this, if you know Akka, you probably know what I'm talking about. That's how you interact with an actor in Akka. But if you use other frameworks like Axon framework, it's very similar. You don't manipulate your model directly, but you send commands that are then delivered to your model that it's managed by the framework at some point. So the commands arrive to your model. So what happens is that command is sent to your model. Your model validates if the command is valid or not. It can reject. It can emit events. The events get persisted. This screen is not following me. I look there. The events get persisted to the journal, and then the events mutate your model. So that's the basic machinery. And the thing is, that's always like that. There is no other event sourcing system that does something different. It's always about receiving commands, validating persistent events, applying the commands, applying the events, and be ready to consume the next command. It's always that machine. So here it's an example of code. And again, if you know Akka, it will look familiar. It's not Akka. This is Calyx. But what I want to show here is just the basic, how it looks like a code that is built on top of event sourcing. So you have a command. You have here add item. Okay, I will check my current state, and if it's checkout, I will just emit an error. Cart is already checked out. If not, I will emit event add item added. That's the event that I will be emitting. And here's the thing. At that point, what is returning here is a description of what I want to happen. It's not happening yet. So the runtime takes that effect that I'm returning here and say, okay, that's a description. I delivered the command to you. You give me back the fact. And the runtime, you say, okay, I know what to, let me open it and see what I need to do. Okay, I need to persist that event. It will persist that event, and it will apply to the model. So it will call the event handler, pass the event that will mutate your model, and you return a new instance of your model, a new mutated version of your model. And then when that is finished, the runtime gives you back an updated cart, and you use it to reply. And in that case here, I'm returning the size of my shopping cart. So I'm returning an effect of integer. Why is that important? Doesn't matter the framework that you use, you're going to have something similar to that. The most important part here that I want you to understand that there are two parts, command handler and event handler, and they are apart. Because I need to have the event handler as a pure function, independent function, because when I replay that model, I will not have the commands. I only have the events. So I go to the model and I take everything that is in my storage, all the events for this model, for this instance, and I use the event handler to rebuild one by one, to apply one by one. So event handler and command handler needs to be apart. So whatever framework you look out there in Java or even in other language, you're going to have this characteristic because they need to be split out. Now, what an event source at runtime needs to do? The first thing it's responsible for doing is entity management. It's not like entity manager in Hibernate, but different kind of management. So if I have a journal and I have a new command coming in for my shopping cart, I have a journal in storage, checkout command comes in, I will instantiate my shopping cart, size is 0 for now, and I will put, okay, this screen is not following the, I always get confused. Okay, I need to look there. So the command is put on hold. And then the machinery behind the event source at runtime, you will have to replay my model. So it reads from the journal, and it applies one by one, and you see that the size, that I'm truly applying my events here because the size increased. And then when I'm at the end of my journal, I can accept the checkout command. It validates, okay, I'm ready to check out. It emits an event, and it's persisted to the journal, and then it's applied. And I put here a representation of what would look like a journal in an event-sourced system. And of course, there are more tables, more columns than that. But for this example, I can only have 4 columns. So I have the ID of my model. I have the sequence number because the events need to have some ordering. I have the type that I have to save it in some fashion. So I need to be able to reinstantiate those events. And what I put here, if you have a base 64 eyes, you can decode it. It's just some base 64 encoding that I put. But what I want what I mean by that is that the payload is opaque. It's just a blob binary bytes that you put on that column. And I just put that to make the point that it's not something that you can read. Now, that's how the theory works. And what I will review here, it's a small trick that we do in the products that we have. I don't know if others have done the same, but the theory is that it goes as follows. You validate the command, you persist events, and you mutate your state. If you're going to build an event source in runtime tomorrow, you can apply this new trick. This trick that I tell you now is that instead, you should do the following. So there is a theory and a practice. You validate the command, you apply the events on your model, and then you persist. And why we do like that? Because if I do like that, I have the guarantee that there are event handlers for the events that I'm about to persist. Imagine if you validate and then you persist the events, and then the runtime is ready to apply the event on your state, but you forgot to define an event handler, that will blow up. And now you have those events in the journal. And then a user sends a new command to it, and what happens? You replay the journal. But that last event that you persisted has no event handler, so it will fail again and again until you redeploy your system. And this is a common mistake when building your own runtime environment, event-sourced runtime. Do not persist events unless you're sure that there are event handlers for that. Of course, developers always mess up things. Of course that people will save events on the disk and then will remove the event handler. And when that happens, you indeed break your model. You cannot reinstantiate it. But at least, if you're building the basic infrastructure, make sure that you first persist. And here's the trick that is important here to understand is your runtime must ensure that while it is processing a command, no other command can be processed. They are piled up in a sort of queue, as such that, okay, it doesn't matter if I applied the events to my model and then I fail to persist it. If I fail to persist because of some network problem, okay, that thing goes out of memory and I have to reinstantiate it. So if it's not persisted, it never happened. And this is a way that we do in Akka and also in Calyx to make sure that you never persist something that cannot be handled, does not have an event handler associated with that. So another important thing, and it's related with the previous one, is concurrent access. Your runtime needs to ensure that only one command can be processed at any single time. So what if I have two requests to withdraw money from an account, and they arrive on my system, and then the runtime instantiates two instances of my account, and each of them will say, okay, the first one will say, okay, 700, I can withdraw 700 because my balance is 1,000, and the other one says, I can withdraw 500 because my balance is 1,000, and now each of them will persist the event, and we're gonna go actually with a balance minus 200. So this needs to be protected. Your runtime needs to ensure that only one command can be processed at a time. Even so in that case here, it got broken. And the magic thing here is, how can you do that even when you have different nodes, different instances from your application in the network, in your deployment? This is a little bit more tricky. And then, of course, both Axon framework as Akka and Calyx, our stuff, and our competitor, we do that. We make sure that even when you have many different nodes, there is only one instance of your model in memory. We do in different ways. In Akka, we do with Akka cluster. I won't really go into details here, but if you build that yourself, make sure that either you have only one node running, or you have some sort of optimistic locking, or you have some cluster technology, because otherwise you're going to break it. And we always start with building event source applications, and then we run into such a situation, say, okay, I didn't thought about that. So that's why it's important to have a framework, a solution for that, because otherwise that can be harder than we might think. And that's also one of the most important thing is, I said that the events go to the journal as blobs, and meaning that I'm serializing those events. And if I serialize data, I need to be able to read it back. So this is something that you have to think from day one. You're going to write bytes to a column in a database. You need to be sure that you can read it back. What will happen is that everything evolves, and your events will evolve. So the first thing, don't use Java serialization. There are many reasons for that. It's unperformant. It's a vector of attack in many ways. I don't use it, so I don't remember. But I remember many cases in the past where it was used as a vector. And it's very hard to evolve. So if I have a payload, a blob in my table, and I read back, but my Java objects change, good luck with that. It's very hard to make it compatible again and to be able to read it back. So you need to favor performance serializations format, and I think about Avro and Protobuf, also because they have a schema evolution. So if you know those formats, they are built to be evolvable. So that, for instance, the case of Protobuf, you add the fields, and if you don't need each field, the name of the field is not important, only the ordering. You start something with 3 fields, and you put a number on that, 1, 2, 3. If you remove a field, you just remove it, let's say the one in the middle, and you have now 2 fields, 1 and 3. And Protobuf, it's smart enough to understand that if there is a payload and 2 it's not available, it can just skip it. This kind of built-in schema evolution is important. most of our customers use JSON. JSON is fine, but you need to have the means to manipulate it before you deserialize. So whenever you serialize JSON, okay, in some cases you can live without it, but you need to have something in place. I'll show you an example. Imagine that in the table I have an item added, something like that, where I have an item ID. So on top I have the JSON format, and I have the manufacturer, completely useless to have my item added event. That's why I put it here, because I don't want to have it anymore. And my model involved, I don't have a manufacturer anymore, and I have a description. This is fine because the manufacturer will be ignored. When you read JSON and you don't have that field on your Java model or whatever, it's just ignore it. So this is okay. And the description gets the default value. But what if you don't want to have the default value? In that case here, the default value for a string is null. I want to have something else. Then I have a problem now. How I will read it back from, how I will set it to not available. So, and that's not hard to build, such a, what I will show. We have it, and if you can build that yourself the way you want. But it's just to give you an idea. We have a kind of item added migration, and whenever we save something from the database, we have a version. And if you say nothing, the version is 0. But once you need to do migration, you create a migration class like this, and you have here the current version. You say it's 1. And here's the trick, because in Java with Jackson, we have this JSON node intermediate abstract tree that I can manipulate. So before, when we read the event, before we deserialize it to the model, we can manipulate it. And in that case, I say, okay, if the version is less than 1, so the previous version, according to my current version, then it means that it does not have a description. So I will add the description, and I will put the default value to not available. That's it. When it reaches my model, the description will be filled. So I hook just before I deserialize my model. That's one thing. And then at the end in the table, I will have something like that. Item added. When I have no version, we'll have nothing, like by default version 0. Or if I have a migration, I will save on the table something like item added #1 to indicate that this payload is starting from version 1. So in that case, it has the description. And you can also modify, I don't know if you saw, in the table here I have quantity. Now I have quantity in full word, not abbreviation. And here I'm saying, okay, now I'm on version 2. And if on that version, if I'm before that version, I will read the quantity, the QTY, and I will set the value to quantity, and I remove that field from the JSON. So you're just manipulating, patching the JSON before it reaches your model. That's one of the things that we can do. But to be honest, prefer protobuf, because at the end it's much easier to deal with. But it's easy to deal with when we are talking about schema evolution, but there are other concerns. So most people prefer JSON, but then you need to have such a structure of something that helps you to patch your JSON. So just to recap, what are the event source in runtime? What the event source in runtime should do? It manages the entity. It loads into memory, and it removes from memory. That's also important, because the goal is you load it to memory to receive commands. You don't do it over and over again. You can keep it in memory for a while. And if you're not receiving many commands, or if you are idle for a while, the runtime should be able to remove it from memory to save memory, of course. Event source runtime should be able to replay your events when it needs to reinstantiate. And that's also an important aspect. There are people using Kafka as an event-sourced storage. That's not a good fit for that, because you should be able to go to the store and only select the events for the current entity that you want to instantiate. And that's not how Kafka is built for. It's not how the topics are built. You cannot create a topic per possible entity that you're going to have in your system. So there is a mismatch there. And there are some ways to work around it, but they all feel like a hack. So you need to have an event store that is able to select only the events for a given entity, for a given ID. Of course, your runtime should be able to receive the commands and deliver to your model, but also hold the commands. So commands needs to pile up in order of arrival while you are replay and then deliver to your model. Also important, when you persist, needs to be atomically and in order, because you need that order to replay it. So the event store, your system needs to guarantee that. That's not that hard. And of course, apply to events to state. That's kind of obvious. Manage concurrent access. Same thing about the commands. That's in your event source runtime should be able to hold the commands while replaying and eventually pile up incoming commands, to avoid that more than one command, that two instances are in memory, and that you corrupt your journal. And hence serialization. That's super important, super important. If you have an event-sourced system, you need to have a strategy for serialization. Otherwise, you're gonna mess up. Okay, a little bit, I think I'm talking non-stop. That is one side of the story. That is the event-sourced side of the story, where you're producing events, where you're consuming commands and producing events. But we didn't finish. We have the other side. It's what I can do with the events. I said event source is when your model is the primary consumer of your event journal. You use it to replay your model. But what else? I have now lots of value, lots of information in my journal. What can I do further? So then we have a second kind of abstraction. We have the event source in runtime, and we have projections. And projections are background process that fetch the events from the journal one by one and pass it to an event handler. That event handler here, it's another kind of event handler. It's not the event handler from your model that I showed before. It's something else. And the projection needs to keep track of its progress. It means that in the journal, and I don't know if you remember, there is a column with the sequence number. The projection will keep track with each event it's delivering to you, and will be saving the offset on some storage. So projection is a machine that reads your events one by one, delivered to some place that you define yourself, and each time that an event is processed, the projection saves the offset. All over again, always that. Always the same thing. And that's what, if you never heard about that before, I mentioned here today, command query responsibility segregation. If you have been always puzzled by what is that, why we have this, it's because it's not really the reason. It matches very well with event sourcing, but you can also have command query responsibility segregation without having event source. But today we are talking about event source. So we have the right side on one side, your model that receives commands and emits events, and use those events to build new models that can be used to query, to be able to search on fields that you cannot do on the previous model, on the command side. So you have one model to receive commands and one model to serve queries. And that's the segregation idea, because they are modeled differently. And when you have event sourcing, you can easily build CQRS, command query responsibility segregation. I won't go too much in detail about that. That's all that I want to talk about CQRS. But if you ever wonder what is that, actually, that's just about this kind of construction. So back to the data. Now I have a journal, and I want to query my data. Give me all shopping carts that have been checked out. I have a journal, and my payload are just blobs that I cannot read. Or give me the list of top 10 most popular products. I have seen, and like the horror stories, I have seen systems that will, for the first one, would say, yeah, I will search all the unique IDs. I will collect all the unique IDs where there is an event checked out. So it means that this shopping cart has been checked out. I will collect all those unique IDs, and then I will replay one by one, and I build a list of shopping carts, and I will return. That's terrible. That you can do that for 10 models. More than that, you're gonna be in trouble. Okay, more than 10, it's okay, but 100, 200, 500,000, you'll be in trouble. But I have seen people doing that, and it's a terrible idea. The other thing, even more hard to solve, is give me the top 10 most popular products. I don't have this information here. This information is hidden inside the payload of my events. And I also have seen that people using Postgres with JSONB, where you can save JSON on a table and search an index, but that's not efficient, or that's a little bit clunky for this kind of stuff. So what we want here is take this information and project to something else that we can query. And we're going to do it in the most efficient way that we can imagine, and we're going to build it. That's when we call it a query optimized model. And we're going to read it, and we're going to produce new data. So the first time kind of projection will be something that, again, it's kind of a small machine that you're going to have in your system that reads events and deliver it to some place. And in that case here, I will build some CRUD model, some view, something that I put on a relational database. And because I'm doing that, I can save the offset in the same transaction as the model that I'm producing. And in that case, that projection, it's exactly once, because the offset is that is keeping track of the project is happening together with my model. That's a luxury, that's nice. And it works more or less like that. Here, the view payload, I put it in clear, but usually on the table underneath, usually it's also a serialized blob. We're going to replay that journal in that model until, but we have a column here. That's the column that I want to search. Give me all the cards that has been checked out. And now I have a representation that I can query. Because you cannot query inside your models. You can only the right model. You can only access them by ID to send commands and so forth. But you cannot query that space. You need to create a different representation. One thing that when I mentioned that I worked previously at the Flemish government, in one of the agencies in the Flemish government, one of the things that we were doing that is that our models were built for screen. We want to display JSON. So what we would put here in the payload was pure JSON. And when you search for a checkout, we are not building an e-commerce application, but just to keep the example, if you search it, given the checkout, we just took the JSON that was in the blob and just sent it to the screen. We didn't need to bring it back to some Java representation and then back to JSON to go to the screen. Direct from the table to the screen. And that is what we call a query optimized model. You build exactly what you need to consume. And you put the columns that you want to search for. And if you want to produce PDF, do it. Produce PDF and put it in some place that you can find it using some index, but don't generate the PDF on the fly. Of course not, it takes too much time. But JSON, it's a little faster than PDF, but still, you don't need to create a different representation than the one that you need to have to display. And that's the sense of query optimized views. Okay, this is just about views, but we can do more. A little bit of code. Again, this is just an example in Calyx code where we have an event handler, and it just get an event checked out. I will fetch my current state I will update it here. I said, okay, checked out, true, because that's the event, and I save it back. Again, your code is only that, because the runtime is doing all the machinery behind for you. All the dance, all the complexity is done by the runtime. The runtime that you write yourself, or the runtime that you choose to use. But there is another way of doing projections. Actually, there are 3 ways. We covered exactly once. I will show here the at least once. And at least once is you consume events, same thing. You deliver the events to a handler, but that handler, it's not a transactional system. It can be Kafka. It can be that handler will take the event, transform to a command, and send to some other entity. It can be just another system on the internet. You don't have a transaction. In that case, you cannot save the offset together with the product of your event handler. In that case, you have to save it later. So you do the call, it returns, and you save. And here, you get in trouble, or you need to be aware of that. Here you have at least once delivery, because it might be that I send my event to some other system, I transform to a command, and I send it, and I get a timeout. I don't know if the other side receive it or not. What I'm going to do? I will save the offset. If I save, it will not be replayed. Maybe the other side receive it, maybe not. I don't know. We cannot know. We are in a distributed system world here. Everything can happen. So in that case, we will not save the offset. Other possible error scenario is you do call, you do get a response, but by the time that you're going to save the offset, you get a network error, and you fail to save the offset. When that happens, this event will be delivered again, because your projection is tracking the offset. The projection will fail. We'll start again, and we'll read the offset table, say, okay, the last event that I need to deliver is that one. That has already been delivered, but you fail to save the offset. So here you have the at least once scenario, and you have to have that in mind, because that's going to happen, and that will happen Friday, 3 o'clock in the morning, when you are in a party, and people will call you. So you need to build for that. And here are 2 more examples of at least once delivery. Again, both from the toolings that we have. It's exactly the same thing, subscribing to the entity's event. This one is just saying, okay, whatever is returned here in this effect will be published to this topic. And this other one is just calling some other service here. In that case, it's the checkout, create order on another one. In both cases, that's at least once. So it can fail, and it will be redelivered, and you have to be prepared for that. The other example that I didn't mention on my drawings is the at most once, because this is less useful, but it can be, in some situations, you might want to if you don't care, you are working on a best effort fashion, that is, okay, whenever I have an event, I save the offset and I send it. And if I miss sending the call to some other system, it's not a problem. I just don't need to do it once again. So you first save the offset, and then you call the other system. So there are 3 delivery guarantees, at most once, at least once. If you save the offset before, you get at most once. If you save after, you get at least once. But if you have the luxury to save the offset in the same transaction as the model that you are manipulating, in case of views, then you have exactly once. Now, this is maybe the last obvious part of the talk, because we said we have a journal, and we're going to consume from the journal. But how? How you do that in an efficient way? I will explain how we do at Lightband. I don't know how others are doing, but they also have their techniques. And that's an important thing, because if you decide to build yourself, be prepared, because this is where things will beat you. When I have a journal, all the events, they go to one storage. I have one system, and they all go there. Here I'm using the shopping cart example, but I may have other models in my shopping cart, in my system, not only shopping cart. And they all go to that huge table, all full of events of all kinds. I don't know beforehand how many entities I have, shopping carts or whatever. I don't know. I cannot I cannot consume according to the IDs that I know. I need to consume in a more generic way. And if I have one projection reading from my events, I have a problem that on one side I have a models producing lots of events, and the other side I have one projection trying to keep pace with all those events, consume them one by one, and doing work. This doesn't work. This doesn't scale. If you have a very small system, it will work. But in most cases, you're going to get beaten by that. So you need to find a way to have different consumers from that huge journal. And you probably think about partitions. No? So that's how Kafka does. No? Imagine you only have one partition in Kafka, you're also slowing down everything with that. So of course it's similar solution, but it's not exactly the same. So let's see how we have done that in a few different ways in Lightband. The one that I show here is the last one, the one that we are quite happy now, and because it solved lots of problems that we had in the previous one. And we do that by slicing. We call it slicing. And we just create a virtual partition in that journal with some number. And how we get into that? It's easy. The ID of my model is stable. So we take the ID hash code model 1024. So there are 1024 different kinds of slice of partitions, virtual partitions, that I can create out of that. Events from a semi-entity, because that slice is calculated on the ID hash code. It's a stable identifier. So the events from the same entity goes to the same place, to the same slice. That's fine. But also, in one single slice, you have entities from other different, you have more than one entity in that slice, because hash code model 1024, you have only 1024 slice. So they are grouped by a slice. Now, does that mean that we have 1024? I have a question here. How do I manage if I have to? If the events they are in order, so they do go to the same slice. If they have different versions, then you deal with that using the migration part of that. So at the end, on the table, you just consume them in the order they are saved. I don't know if I answer your question, but I can answer that just at the end, maybe. Not at the end, before the break. And I'm here for an hour, I think now. I think I can finish that part in 50 minutes and have some time for questions, and then break, and then we come back. Okay. So you might think, do you want to have 1024 process consumed from your journal? That will also be very, very heavy if you have only one node. So what we do is we create ranges. So let's say that we start with 4 projections, for instance of the same projections, and I say first projection is responsible for consuming events from a slice from 0 to 250, and then from 256 to 511, and so forth. So I create slices ranges that I can consume. And there we go. The first projection takes that slice, saves the offset, and there they consume in parallel from the same journal, each responsible for consuming different slices, ranges from my journal. It's the solution that we have right now. It works pretty well, and it gives us the possibility to say, okay, let's start with 4. But if tomorrow I need 2 nodes, I can split them in 2 nodes. And if tomorrow I need more projections because they are going too slow, I can resize my range, and now I have 8 processes in one node, and I can put in 2 nodes, in 4 nodes. And you can see where we can go. We can go up to 1,024 nodes. We haven't had yet a client that went more than 32 using more than 32 slices range, but we can go up to 1,024. So that's the trick that we have to be able to consume the journal to distribute the journal consumption. I think that's the last part from this last sequence of the slides from this first part. That's an important thing, because that's also when things will break for us. That's called head-of-line error. There is also another term for that. I think it's poison message. So let's imagine that I have here the events. I'm not specifying what kind of events I have, just events, whatever. And I have some projection that is responsible to read slice from 0 to 127. And all those events fall on the same projection because they are all between 0 and 127. They are all on those slices. And then there we go. I read, I save the offset, I move to the next one, I save the offset, I move to the next one, and it fails. And it fails because I cannot deserialize my data, because I messed up. I changed my model, and I didn't add the migration that I need. So I have a version in disk that's not compatible with my version in memory. So I got a problem here. But I have a much greater problem. Is not only the event from that entity that won't be consumed, it's blocking the whole slice range. Everybody in that group all events won't be consumed because we are failing here. That projection will fail, it will start again, and it will fail again. I can only solve it by redeploying my system. So head-of-line errors are terrible. You really need to be aware of that and take care of that and monitor that and be able to react when such a thing happens. The best is to not let it happen, to have it well tested and control it. When the error happens, reading the events in the projection, it's probably because you messed up with the format, because you evolved your event to some format that's not compatible anymore. It can also fail when delivered to your event handler. But here, it can heal itself. It can be that the target of your event handler is out of service for a while, and it will come back. You still have a head-of-line error because that projection won't be able to progress, and the events will start to pile up. You're going to have a lag, like in Kafka when you talk about lag, same situation. But eventually, your event handler will process the events, and we'll move forward. But it can be a program error in your event handler, and it will never recover. You have to redeploy your system. Fix and redeploy. And then you can also fail when saving to the offset. But here, it's most probably something that will heal itself. It's something that you have some network issue between your service and the database, and then it fails. So this is super important to keep your system flowing, because you need data to be flowing from one side to the other. When you have that, it's you got in trouble. Okay, yeah, we are at the end of the runtime projections runtime. Just to recap, first thing is a projection is a background process that starts at the beginning of your application, together with your application, keep running on the background. It manages the offsets for you. Read from the beginning of the journal if no offset is available, or from the last processed offset. In case of failure, it resumes. And it's important to not resume immediately. And for that, we need to have some kind of a back-off strategy where we say, okay, failure, I stop like 3 seconds. So usually what we do, that's configurable when you use Akka directly. If you use Calyx, we have a default back-off, but it's something like that. It fails, we wait 3 seconds and try again. If it fails again, we wait, I don't know by heart, 5 seconds, and then 15 seconds, and then half a minute, and then a minute, and then 2 minutes, and then we stop we need to cap it. We cannot wait for an hour. So why we do that? Because if you're failing because some network problem, doesn't make any sense to keep trying again. But it can be, if it's a real head-of-line error that cannot be recovered, that you reach the period that every 2 minutes, let's say, the projection will try again, and it will fail again, and it will try again, and it will fail again. But that's important because you need to build it as such that it always come back and try again, because it's a background process. It needs to recover. And of course, and I know it's harder, easy said than done, but it's much nicer if you can scale out your projections. And scale out, I mean having this slice, but also be able to spread those slices over different nodes, instance of your application. And then you really can use the machines you have at your disposal. I think this is the last one. Yeah, that's my cliffhanger before the break. So I talk about event sourcing runtime, projections runtime, which are, I would say, the building blocks to build event-driven microservice. They are machines that are well understood. People building this kind of stuff know how they need to behave, and it's a problem that is solved. You just come and put your code in there, connect your code, and let it work for you. But the game is not finished. You still need to learn to understand and embrace the fact that you are in a distributed system and your data is spread over different nodes, over different servers, and you want it to be consistent. And that's what I will cover after the break. Maybe we have some time for questions now. And yeah.
In the practice, you mutate first, then you save the event.
Yeah.
The event has the sequence order, right?
Yeah.
Who assigned this sequence order? Because like in the concurrent world, maybe you will be doing mutations when you handle requests at the same time. These mutations can be done before multiple mutations can be done while you were not able to write the sequence, and this sequence number can be out of order. Then the projections will be different then.
Yeah. So the question is, if I try to reformulate, if we first save the events, how we guarantee that two instances, because if I have two instances of my model running and saving events, that they will corrupt the journal, because I may have two events being saved. Is that your question?
Kind of, yeah. Like you have one instance that is handling mutations, but like at the same time you are writing events, and the events has the sequence order. So how do you guarantee that mutations done on the correct order as the events?
Because after I persist the events, if you have a command and you emit like two events, those events, they are persisted in order and atomically, and then they are applied to your model in that same order. But that's not enough to guarantee consistency. You need to ensure that model, there is only one instance of that model in memory, and that if you're sending commands to that model, the commands are being piled up and be processed one at a time. The other alternative that we have is to allow to have two instances of those events, commands in memory, models, that you allow it in two different JVMs, for instance. But then you need to use optimistic locking, meaning that this one will save, the other one will fail, because the sequence number, you keep the sequence number, and when you try to persist the event on that side, it will fail. In most cases, that it's enough. And you can even say, okay, I have my command, it fails. You know what? I will reload this and deliver that command again. Your runtime can do that. You can say, okay, it failed. I will just reload and try again. And if you have a very heavy system, it can be that you keep trying and you never get the chance to persist your events. So maybe in such a system, it's better to say, okay, I will try 3 times and I reload my model, redeliver the command 3 times. Otherwise, I just give up. It's something to consider. But that is not what is done actually in the current state of art in the JVM at least. I mentioned Akka, of course, but also Axon framework. If you use the Axon server, it's all about make sure that there is only one instance over your cluster. Yeah.
Sorry for taking time, but like,
No, it's
how does it scale though? Like, if you have just one instance handling its mutations?
yeah. So it scales pretty well because those event journals, they are append only. So your application is taking care of the consistency, and you're just adding data. And adding data to a file, to a table, it's always much more performant than reading and rewriting a role. So you just append, and usually they are kept in memory if they are under heavy load, and it's just like a pass to the table. And actually, it performs quite well. There was a question behind that I'm not sure if I answered correctly or completely, but I think the person went for the break. Let's have a break. It's 3:15. We come back at 3, and then we have 1 hour and a half more of consistency. Thanks very much. Okay. I'm not sure if my cliffhanger was good enough. I don't see everybody coming back, but let's start. Maybe people will come back anyway. So I got some questions during that break, and would make me think that maybe there is one thing that was not completely clear. Your event-sourced model is a unit of, let's say, it's an island of consistency. It's always consistent, and you can always talk to it and request its state, and that will always be the state as it is now. It's not event or consistent. And the goal is also to isolate your models and make them, if you need to interact between two of them, you cannot do that in one transaction, sending a command that hits two entities. They go one by one. So you need to deal with that. We're going to cover that right now. And it's about each model, it's in its isolation, it's an isolated, consistent boundary. And that's part of event sourcing, because if you think about that, every time there is a command, an event that goes, it goes associated with the ID of this model. So you only save events for this model. You don't save events for more than two models. So my cliffhanger here was consistency, but I tricked you. I will not talk about consistency, but I was afraid to scare you. I will talk about eventual consistency. And if I have said that before, nobody would return, so that's the trick. So the thing is, you are in a distributed system. You have those models that are in isolation, but that's not enough. We need data to flow from one side to the other. And then we have issues, no? We need to deal with the fact that your model is always consistent, but the data propagation from other parts of your system takes some time. It can be super fast, and it can be super slow, depending on the load, depending on the kind of information, the size of the bytes, the payloads that you're sending. So, but it's not that we are in trouble. It's just that we need to understand the problem. We need to understand where we are and what are the tools that we have at our disposal. So the first thing is, on the event sourcing side, the model, the write model, the command model, you know that once it's persisted, it happened. You have that guarantee. If the event went to the journal, it means it's done. And your model will not receive another command until that happens. So this is a guarantee that you have. And you have a guarantee that when you reinstantiate your model, it goes back to its previous known state. And that those mutations are atomic and only one command at a time. That's the first thing. So I'm talking about the command model, the write model, the event source entity. You choose how you want to call it. But that's the side that is producing events. That's the first guarantee. The second guarantee that we have, and that is not always what we It's a little more fragile, or the projection runtime. So events are guaranteed to be read in order. That's okay. That guarantee you have. But event handlers can fail, offset persistence can fail, but when the offset is persisted, you have the guarantee that this event won't be delivered once again. So the guarantee here is a little bit weaker because it's at least once. You can emit this event more than one time, more than once. So, but now you know that you have those two properties and you need to play with them. So the first thing that shows up when you are dealing with event consistency is when you're building your query model. Because your model is producing events, and you're building a view representation, materialized view on the other side. And there will be some delay between the moment that this event was persisted and that method returned an acknowledgement that the command was accepted, and the time that this event is propagated and projected to some query model. That will be event consistent. So I have this example here. I have to apologize two things. First is it's clear that I'm not a front-end developer. What I'm trying to build here is some UI thing. The other thing is that I chose this example, and I had Janis Joplin, Bob Marley, and Jimi Hendrix, and equivalent email, and then I realized that those people never got the chance to have an email address. So I changed it to some relatives of Janis Joplin, Bob Marley, and Jimi Hendrix. But the thing here, jokes apart, let's say that behind this formula, web formula, well, beautifully designed web formula, you have an update method an update for this model where we're going to change the email address from originally is John at Acme, and will be John Hendricks at Acme. By the time that I hit that button, my model is updated, and the event needs to propagate to that view, because on the right side here, it looks like a database table, but let's imagine it's because my pure design skills. Let's imagine that it's a screen on your web browser that shows the list of users you have of people working on your organization. It will take some time before John Hendricks' email get updated here. The thing is, in the CQRS world, people are sometimes very dogmatic about that. If I want to have a formula that updates my model, you have two options here to avoid this problem. Is after you hit the update, you can show the object updated. And at that moment, you can use your write model, your command model. You can do that. But if you click on the update and you want to perform the search just after, move to another page and perform the search, then that will be event consistent. And this is one case of use of views that you may feel like, this is not so convenient. The thing is, yeah, okay. No, yeah. So the writes to command model are strictly consistent. It's always correct. The projection may have some delay. Now, you can use the command model to build individual pages. If you jump to the search page, then it will be event consistent. But you can instead, when you click on the update, you can just show what has been updated. Is that according to the rules of CQRS? No, it's not. Because the whole idea of CQRS is to have a different model for your commands and your view, because they have different needs. But if you have this situation, and that's a big problem for you, don't be dogmatic about CQRS. Don't be like I am. I have been very vocal about that in the past. Now I try to be less dogmatic, because I always said, okay, the command model should only have data that I need to validate incoming commands. I should not hold data in there that I need to display. But we need to choose the right solution for the things that we are building. So being dogmatic about that, it's not the best option. if you have this requirement, don't be dogmatic. If you are dogmatic about that, then you have to work around. So that's the first thing. So dealing with views, you have to pay the price of event consistency, and you have to work around or accept that eventually the search page will not immediately show the results that you expect. So, but whenever you have the possibility to access a model by unique ID, and that's what you can do with your command model, just do it. Do it. Just read your command model state if you really need to immediately show the state in a consistent state on your screen. If not, just let it go, accept event of consistency, but don't be dogmatic. That's the first thing. Now, that's maybe the more interesting part of now we're gonna go to another direction, not talking about views anymore, but talking about interactions between your different services. So there is something called Saga pattern that is for long-running process in your system, long-running transactions. So it's how we deal with building consistency in a distributed system. You cannot make a command and block all your nodes, all your different servers, and try to make them be consistent in one shot. So what you do is you instantiate something here that will be propagated to some other service that will then do some work, propagate to some other service, and so forth until completion. So the first example, so there are two types, choreographed sagas and orchestration sagas. The first one, the choreographed sagas, I will first summarize the properties of choreographed sagas, then I will show some more concrete examples. So the first thing is, so we learn about event sourcing and projections, the building blocks for event-driven, event-sourced applications. No? So you can build a choreographed sagas only using those two abstractions. You have event journal and you have projections. You have an event sourcing runtime allowing you to consistently produce data through events, and you have projections that will, given the properties of a projection, at least once, no, be able to propagate data to other parts of your system. So you don't need other abstractions than that. And choreography, and that's why the name, it's like different parts are dancing with each other in some rhythm. They are sending events, producing events, and the other are consuming, doing some work, and bouncing back more events to the other side. And that's from where it comes the idea of choreography. And it also means that all parts need to be very well coordinated because they need to take part of this wave of movement, this flow. And one of the properties of a choreography saga is that once it's triggered, it will flow to the end. You can interrupt it, have something that just make them stop in the middle, but usually there is no point of control over that. It's just events flowing like in a wave from one side to the other and back and in all directions in your system. It's beautiful, but has this property that sometimes can be a difficult thing to deal with. Starting by head-of-line errors. If you're only using events, producing events and consuming events with projections, whenever you have head-of-line error, you're just breaking your choreographed saga. Worse than that, if you have, as we saw in the previous slide, if you have head-of-line error, you're not only your current saga, the choreography that is running here is blocked, probably others are blocked as well, because the events they go to the same slice, and you have a projections consuming from more than one entity, and it happens then that one is blocking, it blocks all the others, and everything gets stuck. So this is a major issue with choreography sagas, because you don't have control over that. So you need to be sure that head-of-line errors won't occur. And it's hard to debug because it's just things are just running on its own in your system. Those machines are just run in the background. You can have tracing, of course. You need to have observability when you're building microservices, of course. I'm not covering that on my presentation, but those are things that you need to have in place. But that's just hard to debug if it's just going south. And it's hard to know where they are. Because if you have a very complex choreography, when you observe something here, you say, okay, this event never reached that point in my saga because I can see that the state of this entity is still dead, is still on a previous state. But a second later, it's already there, it's already moved. You don't see it's moving, it's just happening in the background. So it's beautiful. It can be very efficient because you don't need much abstractions than any more abstractions than your event source entities producing events and your projections. But it's hard to operate it, to track, to see what is happening and so forth. But it's beautiful. I think it's the most elegant one, I would say. And it goes more or less like that. Back to the shopping cart. I have a shopping cart with my events, checkout, and then there is a checkout processor, a projection, that will consume this event and create an order. And here I put this triangle to show that when this checkout processor consumes this create order, it needs to be idempotent. Because if it fails, I will have a head of line error. So this processor, checkout projection, let's say, it receives the checkout, it needs to create an order, and it must ensure that it won't fail. It can be that it creates the order, it gets a timeout, and this checked out event gets delivered once again, but then the order should not fail if it was already created. The order should say, okay, I'm good. I'm already created. You can move on. So you need to build that in your system, that your models that are participating to a choreographed saga don't fail by this kind of mistakes. And there you go, it's just flow like that. And you go from one to the other, and you have now different parts in your system. It can be different machines, different JVMs, and the data is just flowing from one to the other, but you need to ensure that they are idempotent, because at least once delivered needs to be beaten by idempotency. If you don't have that, you are in trouble. And then you create a head of line errors, and you block all your choreography. I have another example here that's a little bit more complicated, because there is another issue that happens with event sourcing, is that if we take a kind of model that can have a very large journal, so it can exist for a very long time, and you want to ensure that once I send, let's say I have here a wallet identified by AAA, I call it wallet A for short, and I have 200 euros in there, and I want to send a command to it, and I want to be sure that this command can only be sent once. That once the withdrawal happens, it only happens once, that I won't withdraw twice from my account. There are two ways of doing that. Is if your journal can save the command ID, you can have a system that says, okay, this command ID is already in my journal, I will not accept it, and it blows up. Another way is to create a saga, choreography saga. And but we need to create a system as such. And that's just an example. I'm not pretending that this is how you build a transaction of a wallet. I just came up with this example because it will be useful for me to show some errors and also evolve on my next part of the presentation. But imagine that I want to ensure that a command can only be delivered once to this wallet. I cannot keep in the wallet the list of all commands that have been accepted so far, because that will grow and my state will be too large. And I will have a memory limit that I will reach at some point. So I don't want to do that. But I want to have something that protects me from that. So this is the saga that we're going to build. Instead, the choreography saga. Instead of just accepting a command directly to the wallet, I will put something in front. And that something, it's like a service that will first create a transaction mediator. And in that transaction mediator, it will say, you have a randomly chosen ID, ABC, and one participant. It tells the transaction there will be one participant here. After that, I send another command to my wallet, and I say to the wallet, here's a withdraw command, amount 100, and I will just go back here. I put in bold the ID ABC to show that what is in bold at that phase of my process is what will guarantee idempotency. If I delivered twice the command creates, the transaction mediator will say next time I'm already created. I will not. I have nothing to do. Just respond to the command without failing. So that's the guarantee. So what is in bold is our idempotency control of Guardian. Then we send a withdraw to the wallet, and here the wallet say it will not withdraw. It will emit an event say withdraw initiated. It's not yet happening. And I have a pending transaction there in my wallet saying ABC, which is the idea of my transaction mediator. If I send withdraw once again, the wallet will say, no, this is a pending command. I don't need to emit yet another event. I don't need to initiate yet another withdraw process. So here I have protection, idempotency protection, because sending commands needs to be idempotent. Now, the previous events, I don't need to deal with that. I just ignore it. The withdraw initiated, I will use it with a projection to tell the mediator, say, one of the participants of that you are mediating accepted to participate, so joined the transaction. And the mediator will say, okay, I have only one participant and it just joined it, so I can initialize the process here. So now there is a conversation between the two parts, agreeing that they are ready to start. Again, I have here again, I have the joined true. The mediator knows that because it emitted the event join it updated its model, so it knows that if the projection, wallet projection, fails and deliver the join command once again, it will be idempotent because the mediator already received it and have information inside it to keep track that this happened already. And now there is a transaction projection that will take for each participant, and here I only have one, we'll take it for each participant and send a command, tell the wallet, in case here the wallet, execute whatever you have pending there. And the wallet will execute the command now, execute the transaction, and will emit an event, balance decrease. And you see that it moved the ABC identifier from pending to executed. I'm still keeping data inside my model here because it's not yet over. And it can be that the projection tries to execute it again, or that there is something coming in and the wallet needs to be able to say either that is pending or it's executed, but I won't execute it twice. So the wallet projection now can say, okay, balance decreased. I'll confirm with the mediator that that other part did what it promised to do. And the mediator will say, okay, I only have one participant, it executed its transaction, so I can consider myself completed now because all participants executed what they need to do, did what they need to do. And now the projection tells the wallet, you're good, you can now remove the cache information that you had in your model because we are over. Sounds sophisticated, complicated, probably, but that's how you deal with this kind of stuff. When you need to let data flow from one side to the other, what you need to do is to make sure that on each iteration, every participant, and here it's a transaction and wallet could be anything else, every participant keeps track where they are in that process. as such that they can guarantee idempotency. Now, imagine that this transaction mediator here could be used for transferring money from two wallets. You have then create transaction, withdraw from this one, deposit on the other one. Both wallets will be communicating with the mediator independently through projections, and the mediator will only move on once everybody joined it, once everybody executed, and every single point the wallets will keep track where they are and will reject or just not fail, of course, preferably not fail when something gets redelivered to them. So I built that a little application to showcase this, and I want to show also when this will fail, because there's an important point to make about this kind of choreography. So, okay, I have it here running already. I won't show much code. I just want to stay in a high level of the system, of the process. So let's say I will create an account here, and I will deposit 50 something euros. And you see that it didn't deposit immediately. There is a pending transaction here, and we can see here on the logs that the communication between the wallet listener and the transaction mediator listener, the projections, worked as expected. It says, okay, this deposit, deposit requested, it was initiated, and then the mediator received the information that participant AAA joined the transaction. I only have one participant, so then the transaction mediator say, okay, everybody joined it, so I can initialize it. It emits an event, initialize, that goes through and do the cycle. And if I check now my balance, I have the 50 bucks there. So now I have something else, and I did it as such on purpose. Let me show you here some code. Here I have an endpoint that gets requests to do a transfer, and it creates mediator creation command saying that it will have two participants. Both are wallets, and there is the command from is the ID of the wallet that I will withdraw, and command to is the ID of the wallet where I will put money. And then I call the transaction mediator and say create it, do it. And then I call the two wallets. And as you notice here, I'm not capturing the return type here. I'm just calling it and letting it go. And I return my method saying, you're only using the transaction that was created. So I don't wait. Those methods are returning a completion stage. I'm not waiting for them or checking if it worked or not, because that's what I want to, the point that I want to make here in this example. So let me go back here. I will send this. I'm a little bit nervous with my demo, because if I messed up, it won't work the way I want. I want to click on the right place on the right moment. So now, let me pause to make sure that I'm doing the right thing. I will create a transfer and send in 25 euros from A to B. And it's passed. Now I have a report of my transaction here saying of my flow. I have two participants. None of them joined because I just created. Didn't have time yet to get them joined. I will ask for the status. And I can see that wallet AAA joined it and wallet BB didn't. And here's the problem. And that's what I want to use as an example. If I go get the balance of a BB, it say not found. And if I go to the wallet, it says, well, I didn't explain that. I did. It was in the slides. When I'm doing a withdraw, and if this wallet is saying, I will participate on this transaction, it needs to reserve funds because it promised to participate on the transaction. So if I had a balance of 200 and you want to withdraw 100, I will reserve those 100 and say, okay, I have funds, so I want to participate. But now those 100 are reserved. And here, that was in the slides, here I had 50 and I reserved 25 and I have a pending transaction. But wait a minute, B doesn't exist. So now I'm blocked. And if I create B, it's created now, still 0. And my A is still pending because I need to resend that command. Because when I send the first time, well, that call here, the deposit failed. I didn't capture that. So I need to send it again. Hopefully, that whole thing is idempotent. And if I send this deposit again, not this one, wait. I almost messed up my demo. This one. Now, I will say at some point that the transaction complete on both sides. So the point that I want to make here, let me go back to the slide. That was the demo. The point that I want to make here is that if you do a choreography saga, you need to understand that all participants need to exist. And if they don't exist, they need to be created on the fly. If you have a command that depends on the existence of one of the participants, your saga will fail. So that example of a transaction mediator works with one wallet. But to make it work with two wallets, I need to make sure that the two wallets exist. And you could say, okay, before sending the command, let's check if the wallet exists. Is that enough? Because by the time that you checked and you see that both exist and you start the transfer, it can be that one of the wallets got closed, the account is closed. And then by the time that the events flow in your choreography, it hits that wallet and the wallet say, no, you cannot deposit here or withdraw because I'm closed. But the other part already said that it's participating. So you need to be able to track that out and be able to cancel everything. So a choreographed saga, to recapitulate a little bit, a choreographed saga, it's wonderful tool, very easy. You just use the abstraction that you have already, but you need to guarantee that it will not break. And that can be a hard thing to do in a distributed system because you don't know the state of everything. So in the previous example where the checkout creates an order, you create something. So something here triggers the creation of something there. That's okay, because you are creating something. But in the case of wallet here, you need to be sure that the wallets exist. Of course, you can capture the return of each command and say, okay, if this pass, I move to the next one. If the next one fail, then I need to revert or cancel that and that. All fine. That's how we do. But as your use case grows and you need to deal with different parts in a distributed system, this gets much more complicated and hard to follow. So whenever you do a choreographed saga, I would say make sure that you can create the objects that are either they exist and they are not deleted from the system, or you create them on the fly, because otherwise you get in trouble. And that brings us to the next example, which are the orchestration sagas. So orchestration sagas are much more complex, much more powerful as well, but they give you the possibility to deal with this kind of errors. And because they are more powerful, they are less convenient, or you need to have better tooling for that. So you need an extra abstraction at least. You need to have a workflow engine. And there are a few of them like that. There is one, there are different kinds of workflow engines. And some of them are based on configuration with diagrams that you can design your flow. And they are often converted to some kind of script in some dynamic language that can be interpreted to build the diagrams and be executed. And there are also workflow engines that are based on programmatic just code as code that you just write your logic. There is one that is recently exists for maybe 3 years, temporal.io. You can integrate in your system. There is also Camunda. I'm not sure how Camunda compares to temporal. We also have workflow engine in Calyx, but they are all, in both cases, they're all programmatic. And they have some properties. And the first is they can have state, and I recommend you to have workflow engines that have a state, because the state of a workflow is what you use to track the progress. You want it. It's a central point that you can use to control and know where you are. You can rely on events. You can have a workflow that at some point, and it's one of the next, I think it's the next one. Yeah, this one. I will talk about those together. You can reach a point in your workflow that you don't have all the information yet. So you should be able to just pause it. And eventually, you'll be listening to events that will come and hit your workflow back and say, okay, you can resume from here because that event was observed. But you can also pause a workflow because you need to have some extra input from a user. Imagine you are transferring money, and after above certain amounts, you need at least 2 signatures. So you get one, you do the preparations, you pause your workflow, and then you need to have someone coming back to that, hitting some API where they can add the signature that moves your workflow. So this is so it's much more powerful, but also complex than a choreographed saga, because you need to provide all those facilities, because that's exactly what we want. We want to have more control. And of course, it can be canceled at some point. Eventually, you can reach a point in your workflow that you cannot cancel it anymore. If we take the example of the transactions, if both parts, if you are withdrawing from one account and depositing another one, it can be that both parts tell the mediator that they will join. At that point in time, you cannot cancel anymore because events are already flowing in the background, and money will be withdrawn and deposited, so you cannot cancel. But as long as one of them didn't join the transaction, the mediator cannot initiate the transaction, for instance, and then at that point you can still cancel that. All that, it's you to encode in your logic, of course. And again, a workflow, it's like a projection for me. It's something that needs, once you start, it needs to run in the background for as long as it needs to run. And if it fails, it needs to recover. And it can fail in different parts, in different points. It can fail every single step can produce a failure. Why? Because you're hitting some service. You're depending on some information that you don't have yet. So these things can fail. It has to, again, have a back-off mechanism. It needs to have timeouts mechanism, timers, reliable timers that you can guarantee that this thing, after so many minutes, will be retried, and so forth. And if your node crashed and it's instantiated again in your cluster, that the workflow knows where it was. It comes back and it starts where it was without executing. What was executed doesn't need to be executed once again, of course. So it's more or less the flow. Just to have a representation, it will be something like you initiate a workflow and it transitions to withdraw, and then it's not moving here. It does a call to the wallet, and here we are not doing event-driven anymore, and that's another property. A choreography is event-driven all the way down. A workflow can be event-driven. It can receive events and move, pause, wait for events get in, and the workflow moves further. But workflows, usually they are much more making calls to other service, to entities, and so forth. So here, this step in the withdraw workflow, it will call the wallet. And it can fail, and we want to repeat it again and again until it passes or it reaches a timeout or a maximum number of retries. And if it passes all the transitions, the workflow needs to end at some point. And from that point in time, it should not perform any other action. So it's like a state machine. You transition from one step to the other, and each step has its logic to perform. And the idea is that a workflow should be able to have a timeout, a maximum number of retries. Here I put 3 for the whole thing. But you should also be able to configure every single step to have a timeout and a retry. And eventually, you also want to have a failover. So for instance, you decide that you want to make this process here, transfer money from 2 different wallets, but you say, okay, if it hangs for 10 minutes, I just cancel that. If I'm in a state that can be canceled, of course, then I cancel it, and then I need to execute some action to do some recover. So that's all. That helps you build distributed systems, but it adds also lots of thought work. So one other thing, let me just move next to the, yeah. And as I was saying, you also should be able to pause a workflow, wait for more input before you move. One thing that I think I should have added to those slides is that very often, it's not the case here with this withdraw. I can do withdraw here, deposit there. But it can be that you have a workflow that you do some step, and the output of that step is the input of the next one. So you just chain the steps. I do something, I get some information, it returns to me, and I use that to execute my next step. So there are data going inside the workflow that needs to flow between the steps. Now, those workflow engines that we have nowadays that are programmatically just code workflow that we have in Calyx, that Temporal IO is doing as well, they have one interesting property is that they persist the return types of your steps. So I execute a step, I get something, and then my machine crashed. But either this step will be repeated, and the other side, again, needs to be idempotent. But if I get the chance to persist the return, the value that this call returned to me, before I move to the next step, I persist this information. Because now, if that node that is running this workflow crashes, next time the workflow knows, oh, step 1, I executed already, and that was the return type. That was the value that it returned. So now I go to step 2, and that's the input of step 2, because you're chaining the result from each step into the other one. And those workflows provide this kind of abstraction, and that is kind of be able to resume where it stopped without losing data. And that's an important abstraction for distributed systems, because without that, you end up re-executing lots of processing. So I built that same example here, and that's where we have plenty of time. Great. I'm talking too fast, I think. So I have here another one in which I will produce the same error as before. I will create an account. It's there. I will put money on it. I'm using this transfer mediator thing. But then I will do the transfer. Okay, I already started. So it's not passing because the account B, that here I call it BB1, is not there. So it's failing. It's failing because the account doesn't exist. And here's the thing. Because it's a workflow, I configure it as such. They say, okay, you try it 5 times. Actually, if you count it, it happens 6. So you try one time, the first time, and then it retried the steps 5 times more. And then it says, okay, I'm good here. I can stop this. And it just cancels the transaction. And if I go back and get the balance of A, it still have the $50 there. And now I can create B, and I will recreate my workflow. I recreate it here. And it should now, yeah, both transactions completed. But then I have this, let me show you how that is, how that look like. So it's very similar to the other one, except that I have, on each point, I have, here is the definition. I say I first create a transaction, then I do a withdraw, I do a deposit, I have a cancel step, and I chain them all, do that, then withdraw, then deposit, then I register the cancel, but the cancel is not chained. It's, if you see here, after deposit, when I do the withdraw, I transition to deposit, to the step deposit that will do this one. And here I end, or it hangs, like in the example, and then after a while, after I try it 5 times, I cancel it, and it hits this one, and the workflow is canceled. So all these abstractions are needed if you build the distributed system, because you need to be able to control where you are and what is the next thing to do in case of errors. Now, the truth is, and I can reveal that it's not a secret, the workflow that we built in Calyx is just event sourcing. What is inside is event sourcing. So actually, if you don't have your own, if you want to build an event workflow engine, and you have already event sourcing in one side and projects in the other side, you can build a workflow just using those abstractions. But it's a little bit harder. You have to understand what you're doing. But it's just built on top of that. At the end, when you use our workflow, it doesn't feel like event sourcing, but underneath it's event sourced. So to bring it back here, the 2 characters, what are the characteristics of choreography and orchestration, and when to choose them? So choreography, event journal plus projections, that are the abstractions that you need. It moves like a wave, it's beautiful, it's very elegant actually, but you need to watch out for head-of-line errors. It can be hard to debug, hard to track the progress. On the other hand, on orchestration, you need a little bit more of abstractions. You need something more powerful, because you need the central point to control everything. You can have state, and actually you want to have state, because that's the state here is not the state of your entity, it's the state of your workflow. You save in the state of your workflow, you save where you are, what are the steps that have been executed. The workflow by itself will also keep track what has been executed already, but if you want to make a request and ask a workflow where you are, it's the state of the workflow that you return, and you can save on that state which step you are. It's on you to build this kind of stuff. I mean, to define what you want to put on the state. Usually what we put on the state of a workflow is to track the progress. So it gives you that points to progress, to track the progress. You can also have projections that hits your workflow back. But watch out, maybe I haven't said that before. Workflow is also a machine that keeps going, moving from one step to the other. So if you want to listen to events and let those events hit your workflow, you usually want to do that in a way, in a moment that you pause your workflow. So basically, you execute a step, and you say, when this returns, I pause. I pause because I reach a point that now I only move further when I receive some events. If you don't pause and receive events will arrive at any given time inside your workflow if you are not pausing it. And your workflow is moving, and events are coming. So you increase the complexity, because now, while your workflow is moving, it's also getting events being delivered to it, and you need to juggle there. You say, okay, this event I can ignore now because I'm already further on my step. So it's nice to have a workflow that receives events, but I would say it's much easier when you pause your workflow and use the events to resume it. Don't let it go and receive events at the same time. Maybe there are some use cases for that, but I would imagine that will make things much harder to control. And then, of course, cancellation, pause I already mentioned, and it needs to recover from failures. That's also the case for choreography, but that you get already for free, the recovery, because it's based on projections. When a projection fails, it retries. So at the end, the choreography has built-in recovery mechanism. It's just the flow of your events flowing from one side to the other that makes sure that it will reach completion. While a workflow is really like an instance that gets started at some point in your system because of some input. An orchestration saga starts with something that happens that it creates it. And if it fails, you need to have the infrastructure to bring it back. Because when I say failing, it's not like a step failed. It's your node crashed, or your node was moved in the cluster for some reason, because that's how distributed system works. You have nodes that got scaled out, the scale down, and you create instance, you have something running here, all of a sudden you don't have this machine anymore, it needs to be instantiated in another place. So when you move those instances, your system needs to be capable of knowing what are the workflows that were in progress and bring them back into memory. Okay, we have a lot more, 40 minutes. I think I have some content. Let's talk a little bit more about this then. So I have this image in the beginning, and but of course this is very far from reality. You don't split your microservices that way, every single service in one individual machine. But whatever you do, you end up letting data be flowing from one side to the other using events. If you have this topology or any other, if you're doing event-driven, you can also end up with something like that. In this example, I have on one side an other service, I have 3 instances, and the other side I have what in the previous one was a catalog and a stock item service, product catalog and product stock item, but now they're running on the same physical instance, and I have 2. But the abstraction of event-driven that we have been talking about, producing events and consuming events with projections, it's the same. Doesn't matter if they are independent service or if they are just things running inside the same service. It can be the product catalog talking to the product stock item. They will talk through events. It can be one node of other talking to another node, and it will be truth events. It could be the other service talking to the product service, it will be truth events. It's always the same abstraction. The only difference here is that when I'm inside the same service, I'm able to subscribe to the events from another entity directly, and I'm on a separate service, I have to go through some event bus, like Kafka or Google Pub Sub. So this is the point that I would like to make is that we have 3 things here. We have strict consistent event models, domain models. We have at least once projections. We want to make sure that our models are idempotent, so the projections, the fact that the at least once projections will not break because of idempotency. And we have now a fabric which everything is based on events that I can use that same abstractions to let everything communicate between all the parts. So it's not only having events flowing from service A to service B, but also events flow inside service A between different entities that lives inside service A. And those entities can be on the same JVM instance or in separate JVM instance if I scale it out. One other thing, so the difference here is that I'm using an event bus to let those 2 separate services to completely different applications communicate with each other here. But the reality is, why I can't just do that? Why I need to have a broker? Why I need to have yet another piece of infrastructure to let my events be transmitted to the other side? Well, there are a few reasons for that. The first is you don't want, for instance, if you have the product service consuming from other, you don't want it to depend on other. You want to create an abstraction where it doesn't depend on other. You don't want, you want it to keep working if other is down. But if other is down, well, it's not producing events to Kafka needed. So what's the big deal? So one other way to do is to offer in both sides, whatever needs to publish events, gRPC interface that can stream events. The advantage of doing that is that, you know, when Kafka was created inside LinkedIn and they were producing data that needs to be propagated to many, many, many servers inside the organization. And we are talking about a very large organization. And we are thankful to have Kafka because it solves lots of problems. But sometimes you don't need to have a Ferrari to go buy some bread. It's a very powerful tool, but sometimes you just need a channel between two services to consume data from one to the other. And it's okay if that other service is not reachable now. Later it will come back and I will continue producing. So it will be great if I can just consume from another service through some streaming API without having the need to push data to some event bus. And we have been working on this kind of abstraction to make it a choice. If you have the needs of Kafka, of course you should go for that. If you have the need to use something like a Google PubSub, go for that. But if you are just willing to consume events from that other service that you deploy yourself just next door, maybe you just can do that over gRPC. So we have been working on that, and I think that is something that will also show up in other products out there, because it's just simplify the deployment. Okay, frameworks and develop platforms. I have already hinted a lot about the things that we do, but there is more on that. The first thing, and I think I have already shown that image many times, but what I want to call the attention here is that whatever is in there, the only parts that I need to implement as a developer are these two green squares. All the rest is always the same and the same and the same, and it's always doing a very boring work. That this problem has already been solved. And I can only bring my own business logic here. And like Hibernate and the crude words in Java, it didn't show up from day to night. Those technologies have been cooked for a long time, and it's very stable and very popular nowadays. I'm talking about JPA, Hibernate, and they are great. But there are other ways of doing persistence, like I have been talking about. And what happens is that other companies, and Lightband is one of them, are bringing up this kind of solutions to make it easier to build event-driven system. But there is one more trend is, and if we build a cloud that do all that for you, and you only bring your business logic. And so there is a trend, and maybe we are building such a thing. So maybe that's the reason that I see every single week someone in our Slack send a link about yet another developer platform. And developer platforms are usually large organizations build their own internal development platform, so you have the operations teams that defines everything. Even when I was working with the Flemish government, we have our operations team that will define everything. We could just say, I want to deploy this application, and I need to have a database of this type. I need to have Kafka. I need to have that and that. We are not using Kafka anyway. It's just an example. So you just go in and you tell your operations team what you need, and usually they have already everything in place. If you ask something new, they will prepare for that, as such that you as a developer, you just deploy your application with some configuration, and it just works because someone is taking care of the developed platform, the infrastructure for you. And we are seeing lots of companies building developed platforms in the cloud that you just go in and you have, okay, I bring here my Spring application, I want a Postgres database, and this cloud provider provides everything for you. So this is a trend that I see happening. Again, since we are building our own developed platform, that's probably, we are biased and we are hearing too much about that, actually. But just to give an overview of what exists in the Java world, so I have mentioned the Axon framework. They also have like a cloud offer. So the Axon server, it's like a journal, and it takes care of the distribution of your entities and so forth. And you have the Axonic, I have trouble to say, because it's Axon IQ, but they pronounce Axonic, I guess. Axonic Cloud, which is a cloud offer for to bring your application. You code your application using their APIs, and you deploy in the cloud. Then there is Dapper, which is quite different. I don't know who ever heard about Dapper. Okay, not a few, but some people, yeah, not a lot, a few people. So Dapper is a developed platform. It has all the abstractions. When you want to connect to some broker, you bring this module, and then you just get it access to it and so forth. But your platform team still needs to take it over and deploy it in your cluster. So you, as developer, you need your operations team to install Dapper and bring in all the parts. But it's all about having an actor system, dealing with event sourcing, and building all those abstractions that I have been talking. And of course, since I work at Lightband, I will also mention the Akka toolkit and Calyx. But Akka, it's like we don't call it a framework. We call it a toolkit because it's really about going to the shelf, taking all the pieces that you want and assemble that yourself. And we realized that this is rather hard to do for most people, and that's why we built Calyx, which is just abstract away everything. You just bring your business logic. The thing is, those frameworks, toolkits, and developed platforms that I mentioned here are those that are dealing with event sourcing. There are much more developed platforms out there, or frameworks, but they are not really focused on event sourcing. Those are. So if you want to check it out, you have a few options here. Of course, you know which one is the best, so you don't need to lose your time. Okay, a little bit about things that I have seen, and that if you're building this kind of system, it's better to avoid. The first is event sourcing is cool. I will start it just after the Vox. Just don't do that. It's not how you're moving into that. So sometimes CRUD, and I'm just like, my whole presentation, I'm just going against it now. But sometimes just old CRUD is what you need. Just don't exaggerate. Don't go for event source if you don't have that need. And sometimes in your constellation of microservice, some of your service doesn't need to be event sourced. Again, event sourcing is about your model inside your service that produce events to be consumed. But you can have service that just consume events from the outside, but inside is just CRUD. Like, you don't need to have a report application that is open event source. You're just producing PDFs. Okay, so just don't exaggerate there. Don't use it everywhere, because that's not the way to go. So that is the golden hammer anti-pattern, I would say. And then there is this one, the fake event-sourced entity, or aggregate, if you prefer the domain-driven development, domain-driven design concept. And the fake one is that entity that has no business logic. So events comes in, commands comes in, and they just go to the storage. And very often they are just a copy of the commands. Command, copy, event, storage. You don't need that. You're just making your life harder than necessary. It has zero business logic. An entity, it should be able to reject a command. If you find yourself accept everything and just put filling up the event store, you're not using event source, you don't need it. Why I say that is because I have seen people consuming from Kafka, sending the whatever message was coming from Kafka, building commands, sending to entities, doing nothing in the entity, just persisting the events. And then putting a projection on the other side, taking the events from that projection and putting Kafka. They were just transforming the events, the message that were coming from this Kafka topic, and publish it in another Kafka topic. That's not event sourcing. If that's what you need, you just consume from this Kafka topic, you transform and put it on another one. You don't need to build event sourcing engine for that. That's just like crazy, and I have seen that. And that's my favorite one, is, this Who Wants to Be a Millionaire TV show. I think there are people here from different countries. I think everybody had that in their country at some point. And there is a moment that is a quiz, and you have, if you don't know a question, you can call one friend. And the joke here is that event source entity has no friends, it's self-confident, and can always answer the question by its own. When you find yourself inside the event sourced entity and trying to reach a view or some other system to make the decision if it's time to emit those events, then you messed up. Your entity should be able to answer that question with either the data that comes inside with the commands or the state of it, because that's this isolation transactional boundary that we want to build in our system. If you don't have that, if you're dependent on something else, it's because you are not a consistency boundary. So instead, if you need data from outside, you go fetch it before you reach the entity. So in a controller, for instance, you receive some request from the outside, you go fetch some data, you take the request, you get the data that you got from somewhere, you build a larger command, and you send that data to the entity. And the entity should be able to operate to answer that question with only data in the command and data that is in its own state. If you do something else, you're calling a friend, and you should not. And of course, if you have, I think I messed up with this slide. Let's see. Of course, if you talk about the anti-partners, let's talk about the good, the bad, and the ugly. Every time that you read about event sourcing or event first, everybody will say, create events that make sense for your business, that has value for your business, that are meaningful. Here, the example is I have a raffle. The raffle can be created. I add a price. I decide how many participants I can have. I can add participant. I can remove, and can I select a winner. Those are events that express what can happen on my raffle. Now, if you are emitting an event like raffle updated, and you're passing all the participants and eventually the winner as well, like, you're not helping anybody with that. If I'm consuming your event, what should I do? I cannot know what happened in your system. What should I do? Should I keep track of all the participants, and I see the first list of the new list of participants, and I need to make a diff and infer that you removed someone or that you added someone? That's just bad. That's not event sourcing. Event, of course, yeah, technically it is, but you want to express the mutations in a meaningful way, not sending like something like that. And the ugly one, and that's debatable, because it's when you emit events that are intended to be exceptions. Of course, you can emit such events if it makes sense in your business, for your business to have such a thing. For instance, I can, if a participant tries to, if I have a participant that is always trying to subscribe to my raffle more than once, I can keep track how many times this person got rejected, and then I can exclude that person from the system eventually. Just making up something here. But the horror story that I saw with emitting events to express failures is the following. And that's related with the world where I live, where a lot of people are using Akka. In Akka, there is this thing that we usually the pattern that we promote when we talk with an actor is fire and forget. You send a command and you don't wait for the response because we want things to just flow around and happens very, very fast. And there was a customer of us that were just saying, no, Aka is fire and forget. I never ask if a command was accepted. So what they were doing is they were sending a command, and then the entity were persisting if it was accepted or not. And those commands were then being published to a Kafka topic with a projection, and then the guy that was sending the command was listening to the Kafka topic to know if it was rejected or not. So they were creating a very complex, inefficient flow in their system just to avoid to receive acknowledgement from the actor, from the entity they were talking to. And that was like, I have to confess that I flipped this to a few times. I don't know which is the ugliest and the worst. And this version of the slides, this is the ugly, but I think it's quite bad to use events to express exceptions. Anyway, let's move on. Key points. So, yeah, I will have some good times for questions. Let's see. I've been talking about that. Entities as transaction boundaries. They need to live in isolation, and they are strict consistent as well. But that's a good property of them. We can only beat at least once with idempotence. That's very important. So whenever you're consuming from projection, make sure that the other side is idempotence. Otherwise, you're gonna deliver, at some point, you're gonna deliver an event more than once. Choreography is great for linear flows that can't fail. And I guess that some of you think, okay, famous last words, everything can fail. Yeah, but you can create protection for that. But keep that in mind. It's a linear flow. You go from one thing to the other. Make sure that everything exists or can be created on the fly. Otherwise, it will fail. Choreo orchestration gives you fine-grained control if when it's needed. Now, understand the mechanism behind it. Understand the pattern. Embrace it. That's very important. People start building event-sourced system without knowing inside out what needs to be done. They build their own engines and they messed up, or they rely on the wrong abstractions, or they don't take in consideration those things like idempotence, at least once delivered, serialization, that's super important. So follow the principles, apply discipline, which is a very hard thing to ask for developers, apply discipline. We have been saying that since the beginning, and it's not happening yet. And you are allowed to diverge. Don't be dogmatic like I have been in the past. Allow yourself to diverge, but do it when you have a good reason, when you understand what you're doing. So don't diverge at the first week of your journey into event-sourced applications. And I want to close my talk with this Groucho Marx. I don't know if you know this guy, it's a comedian. I like this very much because those are my principles. If you don't like them, well, I have others. So don't be that dogmatic with the principles. Be able to find yourself, if you find yourself in a place that it's impossible to move forward because of those principles, build up new principles, but make sure that they are still sound and solid according to the main principles. That's all I had. If you want to, I hope this is enough information for you to start building your own event sources and projections runtime. But if you don't have time for that, of course, you are invited to check out what we have been doing. The first one brings you to the developer experience to get started with Calyx. The second one is the source code in GitHub from the demo that I did. And if you look in the code, you can get a feeling of how to build a choreography and orchestrated saga. That's all that I had. Maybe we have 50 minutes for questions, which is good and good timing. Thank you very much. No questions? Or you guys shocked? Or Okay, good. I will be here until Thursday. If you have questions you want to talk about, I will be around. Just reach out. Thank you.